section 21. Now it's basically just the metric topology again, but some more properties. And mostly it's think of it as the intersection between the metric topology and the continuous function. So essentially it's section 20 and 18 combined. And yeah, the first page is basically all covered in the exercises. So I'm just going to skip that. And yeah, we have the first theorem, which is, let's see. Yeah, the definition of, yeah, so we have the epsilon delta continuity with respect to the standard topology, and we can essentially extend that to any metric. So it's a stronger version of the epsilon delta definition that you know. Yeah. And essentially it comes down to the equivalence between the criteria of 4, which is, for all x belongs to x, for all v of f of x, there exists u of x such that f of u is contained in v, right? So I'll just state the epsilon delta criteria as well, which is, sure, why not? For all epsilon greater than 0, there exists a delta greater than 0 such that for all x belongs to x. So this doesn't really matter. It just cancels out in a way because we're fixing the x either way. Yeah. D x x comma y less than delta. So yeah, I think the book had a bit of a typo. It doesn't have less than delta in my book, but doesn't matter. So yeah, if we show that both of these are equivalent, then we're done. All right. So yeah, the book has a proof. So I'm just going to explain it intuitively. So yeah, so for all epsilon greater than 0, okay, first let's try 4 implies 5. So if we have a neighborhood of f of x, then we have a basis element which would be of the form of an epsilon neighborhood, right? Ball, whatever you want. Yeah. And there exists, yeah, so there exists a u of x such that f of u is contained in V. And note that since u is an open set in a metric space, we have an open ball that's contained in it, and we can choose that delta, and that serves as our u. So yeah. And for the other one, sorry, what we, yeah, essentially, I mean, I don't know which way I actually ended up proving, but V corresponds to the ball. It contains it or is it, and this corresponds to U or contains it. And you check whether it contains, depending on what part of the proof you require. So yeah. Sometimes I don't really like proving it both ways because the equivalence is just that obvious. Like this screams epsilon delta to me. Like all the quantifiers almost match up. For all D, there exists U, and this is essentially contained in it because this is equivalent to f of x and f of u essentially, right? So yeah, every time this is that's why I consider this the most useful continuity criteria. And this might be the only section where I actually use the continuity criteria that I found most useless, which was the limit point one. Okay, so now we have some countability axioms. So it's exactly what you think it is. Yeah. The first countability axiom is as follows. For all points in a topological space, not metric space here, uh, there exists a collection of open sets UN such that well, yeah, any for all neighborhoods of X, U is completely, what is it, contained or contains? Yeah, contains. There exists N such that U contains UN. And note that any such basis has to be infinite because otherwise you can take the intersection finite intersection of all of them if it's finite, and you'll get an open set, and it contains one of the basis elements. Or it's only possible if there's no neighborhood that's a subset of it. That would be a weird space and probably not of interest. Like a finite space would satisfy the first countability axiom trivially that way. A finite space being a space with finite open sets, a finite amount of open sets, like the trivial set. So that would satisfy the first countability axiom trivially, but such spaces are not interesting. So for the most part, we need a countably infinite amount of open sets here. Yeah. And the reason metric spaces satisfy this axiom is because you can simply take ball of 1 by n, ball of radius 1 by n. Yeah. Because no matter what open set you take, it's going to have a ball of epsilon radius around it, around the point x as a base, as a basis. So it's going to be contained in the open set, and there exists an n such that 1 by n is less than epsilon for all epsilon. So yeah. And the second countability axiom, I'll just tell you right now, is we have a countable basis. So, and we all know what a basis is. So yeah, if it's countable, then it satisfies the second countability axiom. And note that the second countability axiom implies the first one because we don't need to care about any points. We can just use this very basis as our set of open sets. And we're using open sets because we want the freedom to choose. The basis element might not help us here. For example, we had a countable basis as choosing A and B to be rational. But what if we want an irrational number surrounded by, 1 by n? So that won't lie in any basis element here. This works for it, but that's why we have open sets. Okay. So now that we have this, I'm going to prove it directly using the first countability. Remove the mess that the book creates by showing using it as metrizable first. Okay. So yeah, if there exists a sequence converging to x, yeah, for all so xn belongs to A for all n, and yeah, is that it? Yeah, A is a subset of x. This is equivalent to x belonging to limit point of A. And this one requires first countability. Yeah. Hang on. Yeah, so I'm going to use snaps to indicate that. And that way you can know from how many times I snapped, how many times I actually checked, and how unprepared I was. Also, I swear it was more to actually refill my ink. Yeah. So let's prove this direction, which holds for all topological spaces. So yeah, xn converges to x. So for all u of x, what does that mean? It contains all but finitely many, right? Yeah. So xn belongs to x, u for all but finitely many natural numbers, right? Okay. Now, how do we show that x is a limit point here? Wait, there's no function here, right? Yeah, not yet. Okay. So, yeah, actually, it's trivially verified because the neighborhood of x is containing a point in A. So, because all of them belong to A. So, yeah, this direction is trivial. Let's go for the other one. Okay, so x is the limit point of A. That means for all neighborhoods of x, U intersection A is non-empty. And yeah, essentially that's it. So how do we work with this? Yeah, so U, we're assuming it has a countable basis. So am I going to cheat? Probably not. Yeah, I'm going to cheat. Okay, yeah. So we have the sequence determined from the counter. Okay. So we can just take u to be un here, and that won't be a problem. And for each un, we can take this intersection to be xn, and this will give us a sequence. And why will it give us a sequence? Because, yeah, yeah. So if we, from this, if we define the sequence, then what will happen is we take an arbitrary neighborhood of x, and we have to show it's a limit point, right? So it's a relatively straightforward lemma to prove that it will actually have infinitely many all but finitely many basis elements contained in it because hmm, okay, that's I just think a bit harder about it. Sorry. Yeah, so sorry about messing it up. Or yeah, so I understood why the book wanted us to work with U1 till intersected till UN, and that's a very critical reason, and that's because that finite intersection is contained in all literally finite of the basis elements, and it contains the other ones. Okay, it need not contain them, but it's at least something. Yeah. So what's happening here? So if we take U1 intersected till UN and then find the xn from here, note that this is going to be an open set no matter how finite you intersect. So even if n happens to be a billion, which it will be at some point, x 1 billion is what? It's still coming from an open set here. This is an open set, no matter what you take. That's one thing. And yeah, so x 1 billion, let's just work with that, is a member here. And yeah, since every open set has to contain at least one basis element, what's going to end up happening is that x from that, so every open set is going to contain un from some point onwards. What's going to happen is since we have taken xn from the intersection of un onwards, so it's going to have intersection of u1 till un plus 1 and then un plus 2 and so on. Xn will happen to all the xn after un will lie in this open set u. So a little bit of extra work is done, but it allows us to show that all but finitely many xn will be in u. And that's precisely because this is chosen, u1 till un, and not just the countable basis itself. So that part is critical. This was not noticed when taking balls of radius 1 by n because simply because they're the same. If you take balls of radius 1 by I as ui, the intersection happens to equal balls of radius 1 by n. Of course, if you go till infinity, it's going to turn out to be the single point, which is close. But as long as you're finite, you're always going to get a ball. Yeah. So that's where the extra work comes in. Okay. Now let's prove the function continuity. Yeah. So f is continuous implies for all sequences converging to x, f of xn converges to f of x. So I actually proved this implication uh, in a specific case by using f, taking f to be pi of alpha. And I showed it in the exercises of product of section 9 that what that yeah, I could generalize the theorem. So I'll just show the proof again, but I have proved it before. So how do we show that? Yeah, if we take a neighborhood of u of f of x or v, whatever, yeah, we take its inverse image. Since it's continuous, it's going to be open and it's going to be a neighborhood around it, x. So it's going to enter, all but finitely many points of the sequence are going to lie in it. And then you observe that since f of f inverse u is contained in u, all of them are going to lie in u. Yeah, that's actually it. I said it orally. I'm not going to write it down. Yeah. For the other one, for the implication, we have to use the previous lemma. Yeah. And the previous lemma uses the first countability axiom for the metric space X. Note we for some reason don't need it for Y. Oh yeah, sorry. F is a continuous function from X to Y. And if X is metrizable or satisfies the first countability axiom, and yeah. Also, a small note. A metric space need not satisfy the second countability axiom. And a simple example is take the power set of R. The power set of R is a topology because it contains or every set is an open set, every subset is an open set, and yeah, the basis cannot be countable because the basis has to be every single real number, every singleton of a real number, and that's not countable. Yeah, yeah. So and it's metrizable by the discrete metric. We've already discussed that in section 20. Anyways, yeah. So for the other direction, let's see, x n converges to x. F of implies f of x n converges to f of x. So how do we show that f is continuous given that, yeah. So this is where the book says that we show that f of a closure is contained in f of a whole closure. Yeah. So let x belong to, if we show that, are we done? Yeah. If x belongs to a closure, by the preceding lemma, it implies that there exists xn converging to x, right? Yeah. So we're using the preceding lemma for that. And now what? Now by this condition, there exists an f of xn such that it's converging to f of x by the condition given to us. What else? So since this is converging, what does that mean? That means, okay, this implies that f is a limit point. Note that this doesn't, so this implication does not require any axiom. It's applicable for all topological spaces. This one required the metrizability of x, or just the first, of course, just the first countability axiom. But this implication is given to you for free. So yeah, and we just proved that x belongs to a closure implies f of x belongs to f of a closure. So yeah, and yeah, we're done because this is the continuity criteria. Okay, I'm not proving the continuity of the addition, multiplication, etc. yet. It's covered in the exercises. And theorem 21.5 is basically just a composition of theorem 18.4, which is, f is f and g are continuous implies f cross g are continuous in the product topology, in the Cartesian product topology. Is that it? Yeah. And since by lemma 21.4, which we'll prove in the exercises, all these operations are continuous, then yeah, the functions being added are also. So yeah, there's not much to discuss here. Then we have the definition of what uniformly converging means. And yeah. Yeah, so first we define what uniform continuity is. So this is where we learn that quantifiers are very important and the order matters quite a bit. So I'll show you how it's different from continuity at every point. Sorry, convergence at every point. So yeah. So for all epsilon, actually I'll write them both simultaneously. So yeah. So this one is uniform convergence and this one is continuity convergence at every point. So for all epsilon greater than 0, Yeah. Here for all, so I'll write one here first. For all x belongs to x. Yeah. Then we have there exists n belongs to z plus such that for all n greater than equal to n, yeah, f of f of n of x, f of, yeah. So this is convergence at every point, right? If you switch them, then you get convergence, uniform convergence. So yeah, I think these two don't matter because they're of the same kind. I'm not completely sure, but yeah, that's what I suspect. Yeah. So the key difference here is that we're fixing the epsilon here. So again, it doesn't matter. But for each epsilon, we're choosing the n, right? Here, for each x and epsilon, we're choosing the n, right? And this is essentially grouped together, so it doesn't matter. Yeah. And once the n is chosen, then it applies to all x, right? So for all x, for all n, this is the case, right? Yeah. And this simple change of quantifiers makes a whole difference because what ends up happening is that this implies this one, I think. Yeah. Because here we have the same band, same n here, and sometimes we can choose the same delta. Is an equivalent definition, but this one does not imply that. Yeah. I do hope I got the quantifiers right. Let me check. That's not greater than zero for all x, and then we'll, yeah. Hmm. And for all n, yeah. Yeah. So yes, the order of the quantifiers matter. And this is the definition of uniform convergence. Yes, yes. Yeah, yeah. Okay. Yes. Now let's prove the uniform limit theorem. So if this and fn is a sequence, okay. So fn is a sequence of continuous functions. So a sequence just means a function, they're indexed by the natural numbers. So yeah, we have each f of n, each fn is continuous, and yeah, from the topological space X to the metric space Y. So yeah, keep in mind this is Y here because we're measuring it along the function and not along X. And Fn satisfies this property. So this one. And yeah, we have to show that F is continuous. So we have to show for all X, for all V of F of X, there exists U such that F of U is contained in V. Yeah. So yeah, the epsilon by 3 treatment that the book does is just aesthetic pretty much because essentially you can choose epsilon to be anything and then get 3 epsilon to be less than epsilon. Yeah. Okay. So choose an n such that, yeah, choose an n such that for x and for x naught. So we're choosing, okay, first of all, we're fixing x naught and we're choosing v of x naught. So we're fixing both of these. And now we're working with these things. Yeah. Okay. So let y naught is equal to f of x naught. That's just there. Am I going to be able to add anything? I'm not. So, yeah, the whole point is that f of n x comma f of x can be used, and so can f of n of x comma f of x naught. Sorry, yeah, and both of their distances are less than epsilon by 3 or whatever you want. This follows from uniform convergence at every point, so we can use it for. In fact, yeah, it applies to all points, and that's precisely what we want. So we chose epsilon by 3, and then we chose the n, and then for x and x naught, since they're both members of x, we got this, and then what? And then, so the x happens to be xn or whatever you want here, and due to the fact that U is open, we have a basis element contained here, and yeah, so why can we choose such a U? Hmm, yeah. Yeah, I'm not going to go more on into it. It's just the standard usage of definitions. So now I'm going to discuss the examples after this. Yeah, so we use the continuity of Fn here because all Fn are continuous. So because of that, we get the third inequality. And from that, we apply triangle inequality twice to get from xn to x naught essentially. Yeah. So it says by choice of Fn, what we're using, by choice of U, what we're using is the continuity of Fn. So that's why we can safely get from x naught to x, Fn of x. And with the triangle inequality price, sorry, we can just add the 3 and get epsilon from f of xn to f of x naught. So from here, yeah, here to here to here, here to, yeah, something like that. And from that, we get the difference between f of xn to f of x naught is epsilon, which is what we wanted. Okay, example. So note that if we wanted to prove that the box topology cannot be metrized, then essentially the method is we assume it can be metrized, and then we arrive at some properties of metrizable spaces, and then we show that this topology doesn't have that property. And it's a contradiction, and that's why the box topology is proven this way to be non-metrizable. And yeah, the argument is essentially a diagonalization, and that essentially we have a sequence of points, and at each diagonal we have the basis defined. And yeah, that basis element is intersecting none of them. It's a neighborhood of 0. So because of that, it's not matching at least one point for all of them. And because of that, it's 0 is not, it's not converging to 0, but it's a limit point. And that's how you show it. So, and it's a limit point because, well, you take any neighborhood, it's going to contain no member of the sequence. Yeah. Okay, yeah, we're assuming it's convergent, and then we're coming up with a basis element that isn't the case. It's not the case. And 0 is it's intersecting with some point or the other because yeah, whatever basis you take, you can take some outside it. Note that we have to actually diagonalize it because what we could if you take something like 1 by n throughout every band, right? The problem that it would cause is that we wouldn't really get a point. We can't get a basis because it would be shrinking everywhere. So a diagonalized box basis element has to be created. Yeah. And another thing to realize is that sequences have a direct correlation with countably infinite. And it's precisely this that allows Rj, where J is not countable, to be non-metrizable. And another way you can look at it is that D is a function from x cross x to R, and R has a countable basis in a way. And it's precisely that countable basis that allows us to make the 1 by n that we needed. And since we can't make that 1 by n for Rj, as you'll see, it's not metrizable, essentially. Yeah, and it had a neat example of taking it to be one at finite points, I believe. Yeah, sorry, zero at finite points as one at other points, and it's a limit point because it's intersecting it, and because of the nature of uh, the whole set being what's containing the whole set being contained at all other coordinates but finite coordinates for the product topology. And yeah, that's why it's a limit point, but it's not convergent because it has to match up at all uh, all of the ones, but it's a countable union. So for each sequence element, we're getting a finite amount of points, and if we take the entire sequence, we can get at most countable. And if you alter it at the at some uncountable point, yeah, and it can be a single basis element at u beta. So yeah, that is after a whole amount of uncountable stuff, countable stuff. So this beta is after that countable union, and yeah, after that you take the product topology element because it's only not the whole space at one point, and yeah, we've gotten a point that does not intersect any of them essentially. So yeah, I mean, I'm just explaining what the book explains. Yeah, if I feel like I have nothing to add, it will look stupid in this. Yeah, let's do the exercises now.